We're looking today at section 4.8, and we're talking about solving higher order polynomial inequalities. We'll do some applications as well. And I'd like to start by using this example. I would like to know, when is x cubed plus 20 less than or equal to 5x squared plus 4x? I typically like to work with these problems like we so often do with our polynomials, by getting 0 on one side. So I'm going to rewrite this to get the form f of x is less than or equal to 0. And so I'd have x cubed plus 20 minus 5x squared minus 4x is less than or equal to 0. Or, if you like the descending order the way we usually write it, we could rearrange that just a little bit to look like this. What I've got for us here is a graph of this function. So we've graphed this polynomial right here. And I'd like us to just see what we could do about solving that inequality, just kind of by looking at the graph. So I want to know, when is this polynomial, as shown in the graph, less than or equal to 0? Well, if I start by just thinking about where it's equal to 0, the zeros of the polynomial I can identify pretty clearly are here at -2, here at +2, and then over there at 5. Right? But where is the function less than or equal to 0? Well, my function, or my y values, are below 0 here. Right? All of those y values are smaller than 0. And then also right in here, all of those y values are smaller than 0. Now my answer has to be in terms of x, right? So let's think what x values correspond to those pieces that are below or less than the 0. Well, let's see, this piece would correspond to all of the x values from -infinity until we get to -2, right? All through there. And since it is less than or equal to 0, I can put a bracket on that. This little section that dips down below 0 corresponds to this bunch of x values. The x is between 2 and 5. So those are the intervals that I would say solve my original inequality. I've already written them, but I'll write them once more here. From -infinity to -2, and from 2 to 5. All right, what if I didn't want to do this problem graphically? What if I wanted to solve the same problem by hand? Let's think what I would need to do. First of all, notice that it was really important to know what the zeros of the polynomial are. So I'd want to start by getting those zeros, or in other words, solving f of x equal to 0. I call that solving the related equation. F of x equals 0. We've had a fair amount of experience doing that in this last chapter, right? Solving polynomial equations like that. All right, once I've solved that, so I now know what the zeros of my polynomial are, essentially what I'm going to have are several sections of x values, right? I'll have a section before the first 0, a section in between zeros, another in between, and then a section after the last 0. Notice that in each section, either everything is below or less than 0, or else in this section everything's above or greater than 0. This section is all below. This section is all above. So if I don't have a graph to tell me what's below 0 and what's above 0, what I'm going to do is I'm just going to pick a test point within each interval. So, for example, here I might have picked as a test point -3. If I had taken -3 and plugged that back into this function, it would have given me, it looks like something like around -40. It would give me a negative value. And I would have then known that this entire section is down here below the x-axis and really is less than or equal to 0. In other words, I would find out that it's true that we're less than or equal to 0 in that section. I could then move over and I could say, what about in this section between -2 and 2? Once again, I could pick a test value, like maybe x equals 1. And if I were to plug 1 into this function, I would find out that I get some answer that's positive, right? It's not less than or equal to 0. And so I would find out that this is false. I would do the same thing over here. Maybe I'm going to pick a test value like, I don't know, 3. We would find out that we do get a negative y value. So we'd find out that that's true. It is less than or equal to 0. And then maybe I'd pick one out of the last interval, something bigger than 5. Maybe I would test 6. And I would find that I get a positive value. That's not less than or equal to 0, so it would be false. So by choosing one value to test in each of my intervals, I can discover whether the entire interval is truly less than 0, or no, it's false, it's not less than 0. And that one test value makes that determination for the entire interval. So that's going to be my second step. If I don't have a wonderful graph to work with, what I'll do second is I'll choose one test value from each interval. To determine whether the inequality is true or false. On that interval. Okay. Third, of course, my final answer will be just the intervals where I got a true inequality. All right, so we're going to solve a few inequalities using this method, and we'll check our answers graphically, but we're going to see if we can predict the answers with algebra first, right? Do an analytic solution and then check with a graphical solution. All right. Oops, I tried to get that to focus better and it focused worse. Let's try that again. I think it's not seeing the words. There we go. All right, so here's my original inequality. Again, I prefer to have 0 on one side. Boy, this is going a little nuts on me. I'm sorry. Let me see if I can find something with more words on it to focus on. There. All right, so here's the inequality I'm trying to solve. And again, I very much prefer to have 0 on one side. So let's get that first. Got my 3x cubed. I'm going to subtract the 4x squared, keep the plus 12x, and subtract the 16. So that's the inequality that I'm going to consider the actual problem I'm trying to solve. It's a version of that. Right? So first, I need to solve the related equation because I need to know those zeros. So I take my function and ask myself, where is that actually equal to 0? Looking at those 4 terms, I'm hoping I can factor this by grouping. And let's see, if I factored out an x squared, would make that 3x minus 4. And here I'm going to factor out a 4, also makes that 3x minus 4. So I have 3x minus 4 is my common binomial, times x squared plus 4. So either 3x minus 4 equals 0, or x squared plus 4 equals 0. Here I've got 3x equals 4, so x would be 4/3. And this one would say x squared is negative 4. So x is going to be plus or minus the square root of negative 4, plus or minus 2i. Now, that plus or minus 2i, remember where I'm going for, right? I'm going for the x-intercepts here. Plus or minus 2i is not going to be an x-intercept. So even though it's truly a 0 of the equation, that's actually not going to be on the graph. So the x equals 4/3 is the only real valued 0, the only one that's going to be on the graph, and therefore the only one I have to worry about. So here comes step 2. I'm going to do my test. What I like to do is just draw a little number line. I'm not going to try and draw the whole graph because that would take me quite a bit. But I'm going to draw myself a little number line. I'm going to put the zeros, in this case the only real one, on my number line. And I'm going to say that with only one 0, it kind of divides it into 2 sections. That's all. Okay? So I'm going to test one value in each section because everything in each section either is truly less than 0 or not, either true or false. So let's pick a test value. I can pick any test value smaller than 4/3. I really like to use 0 as a test value because it's an easy number to work with. So let's test 0. If I were to plug 0 into my inequality, and this is the one I'm testing now, what I would get is 0 minus, that'll be a 0, plus that'll be a 0, minus 16 is less than or equal to 0. That 6 says negative 16 is less than or equal to 0, which is certainly true. Let's pick a test value now on the other side of 4/3. Anything bigger than 4/3 is fine. I'm going to go with 2. If I plug 2 in here, 3 times 2 cubed minus 4 times 2 squared plus 12 times 2 minus 16 is supposed to be less than or equal to 0. All of that, when I simplify it, gives me positive 16, less than or equal to 0, and that is definitely false. So without looking at the graph, I know that any numbers smaller than 4/3, we really will get something below the x-axis. Smaller than 0, my inequality is true. As soon as I go past 4/3, I'll be above the x-axis. That will no longer be true. And so I'm going to finally write my solution then as just the part that was true, from negative infinity to 4/3, and it was less than or equal to 0, so I can use a bracket on that. All right, let's try another one. In B, again, I've got a cubic polynomial, and this time I want to know where that's greater than 0. This has already got the 0 where I want it. I don't have to do that this time. So I'm going to start out by solving my related equation. X cubed plus 2x squared minus 2x minus 1 equals 0. Now, just to save a little space, I'm going to ask you to kind of mentally think your way through the factoring with me. It is 4 terms, so I'd probably try grouping. But if I factored an x squared out of the first pair, I'd get x plus 2. If I factor a negative 1 out of the second pair, I get 2x plus 1. Not the same. So my grouping method's not going to work. When factoring doesn't work, what I have to fall back on is my rational zeros theorem. So I'm going to think rational zeros theorem here. So P over Q. P is the factors of the, first of all of these could be plus or minus. And the factors of 1 are just 1. And Q is the factor of the leading coefficient, also just 1. So not a lot of options here, either positive 1 or negative 1. Let's just quick try this by hand. See if 1 works. That would give me 1 plus 2 minus 2 minus 1. And yes, that does give me 0. And so, if I did my division, I could go ahead and let's see, the coefficients here are 1, 2, negative 2, and negative 1. I'm going to bring down the 1. 1 times 1 is 1, and that adds up to 3. 1 times 3 is 3, and that adds up to 1. 1 times 1 is 1, which adds up to 0. Remainder, 0 as expected. And let's see here, that would give me x squared plus 3x plus 1 as my quotient. So I can get a factored form of this, I just had to work a little bit harder for it this time. X equals 1 was a 0, so x minus 1 is a factor. And then my other factor is x squared plus 3x plus 1. All right. Either x minus 1 equals 0 or x squared plus 3x plus 1 equals 0. This is going to give me that x equals 1. And this is just the problem that keeps on going. This is not going to factor, so I'm going to have to use a quadratic formula. Negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 1 over 2 times 1. It's negative 3 plus or minus the square root of 9 minus 4 would be 5 over 2. And if I'm going to have to put these on a number line to get my test intervals, I probably need some decimal approximations here. So I'd have negative 3 plus the square root of 5 divided by 2 is about negative 0.38. And I'd have negative 3 minus the square root of 5 divided by 2 is about negative 2.62. Right, that one was when I used the plus, that one was when I used the minus. All right, so finally, we've come up with 3 real zeros for this particular polynomial, and I'm finally ready to do my test. So step 2, test. I'm going to put these on my number line. The first smallest one was negative 2.62. The next one was negative 0.38. And then the last one was x equals 1. And that's going to section my number line into 4 pieces. So I'm going to pick 4 test values. And for each test value, I'm going to check to see whether my original inequality is true or false. So let's pick some test numbers. I'm going to go with negative 3. I'm just going to pick all my test values at once this time. And here, maybe I'll go with negative 1. I've got my favorite 0 in here. And maybe 2 out here. Okay. So I'm just picking one number in each of my intervals, each section of my number line. And for each one of these, I'm going to plug the number in here and see if it's really greater than 0 or not. Now, you can definitely plug them in by hand like I did in the first example, but it does take quite a bit of time. So I have no problem with you using like a table in Desmos to do the plugging in. It'll make it a lot faster for you. Let me show you what I mean. For now, I'm going to get this graph out of the way because I'd kind of not like to look at it yet. And whoops, actually, even before I make my table, let me put in the function that's supposed to be greater than 0. My function is x cubed, equals x cubed, plus 2x squared, minus 2x minus 1. And then I'm just going to create a table. I'm going to put all my test points in, and I'm going to ask Desmos to take each test point and find f of x1, substituted into the function for me. So my first test point was negative 3. And when I plugged in -3, Desmos tells me the function is going to give me -4. Now, according to this problem, I want that to be greater than 0, and that is certainly false. Okay, I don't need to see you plugging everything in by hand like I wrote it out up here, but at a very minimum, I do need to see what happened when you plugged your test point in, even if you did it in Desmos. Tell me what the result was. Show me what that inequality would say so I know how you're getting your true or false. All right, my next test point is -1. That gives me an output of 2. And again, I want that to be greater than 0, and that's certainly true. My next test value is 0. I can probably do that myself. It looks pretty clear I'm going to get -1. But just to be thorough, let's put it in Desmos, and there indeed, there's that output of -1. Again, I want that to be greater than 0, but it's not. So that section is going to be false. And then my last test point is 2. That gives me 11. I would like that to be greater than 0, and it is. So my last section is true. So, thirdly, I'm going to write my solution. The places where this polynomial truly is bigger than 0 would be from -2.62 to -0.38. Notice I'm using parentheses because it's just greater than 0, not greater than or equal to. And also, I'm going to join this answer here with a union sign from 1 to infinity. We often use that little answer to kind of join two pieces, or that little union sign rather, to join two pieces of a solution together. All right, this one I've actually already got graphed. So let's take a look and see if we can also see this same solution based on our graph. I got the graph out of the way before, but I'm going to bring it back now. There were those zeros, same exact ones that we found by hand. And we wanted to know where this function is greater than 0. So notice this section in here is above 0, from the -2.62 to the positive, or to the -0.38, first part of our answer. And then this section over here is also bigger than 0, and that would start at x equals 1 all the way out to infinity. So you can graphically see that same answer. By the way, I did express that answer as the rounded decimals, but notice that we could have gone back to the exact values if you wanted to, or more likely if my math lab made you, right? We could have said the -2.62, that was here using the minus. So I sort of said that was from -3 minus square root 5 over 2. And the -0.38, that was from this using the plus. So -3 plus square root 5 over 2. Joined with the 1 to infinity. So I certainly could have gone back to the exact value if I needed to. All right, I know these are a little bit of a process to solve by hand. So let's try one more together here. I've got this inequality that I'd like to solve, and right now it doesn't have the 0 that I want. So I'm going to go ahead and distribute this, 2x to the 4th plus x squared, and then I'm going to bring that over as a -15 is less than 0, And I'm going to say that's the inequality that I'll actually try to solve. So I always start with my related equation. And this time I've got a trinomial. If I'm going to be able to factor this, I would need a sum of 1 and a product of negative 30. And I think it's going to work this time. If I go with 5 and 6, put the negative on the 5, that'll add up to a positive 1. So I have this 2x to the 4th. I'm going to break apart my middle term as negative 5x squared plus 6x squared. And then that minus 15. Now I have 4 terms. Now I can do grouping. My first group, all I can factor out is an x squared. So I'd have 2x squared minus 5 plus, looks like I can take a 3 out of that, also 2x squared minus 5. And I have 2x squared minus 5 times x squared plus 3. All right, so either 2x squared minus 5 is 0, or x squared plus 3 equals 0. This would say 2x squared equals 5. So x squared is 5 over 2. And x would be plus or minus the square root of 5 over 2. Probably want decimal approximations if I'm going to put this on a number line. Square root of 5 halves, approximately 1.58. All right, over here I've got x squared equals negative 3. So x would be plus or minus the square root of negative 3. And this one's going to give me an imaginary result. And I know the imaginary results are not going to be on our graph. Perfectly good zeros of the function. They're just not on the graph, so I don't have to worry about them for this purpose. All right, we're ready to test. I'll put my only 2 real solutions this time on my number line. Negative 1.58 and positive 1.58. And remember that when I pick my test values, what I'm testing is to see if this inequality is true. All right, let's pick a few numbers. I'm going to go with negative 2. And in the center here, I'm going to go with 0. I always like 0. And then maybe I'll just go with positive 2 up here. Once again, you certainly could plug those in by hand. That would be perfectly fine. But it'll make it a little bit faster if I use Desmos to do the arithmetic for me. So, once again, I'm going to kind of get the graph out of the way for now. We'll look at it after we've done our by hand work. Oops, sorry, I always forget to put my function in first. Our function is 2x to the 4th plus x squared minus 15. And my first test point was going to be negative 2. Oops, I forgot to tell Desmos to do f of x1. There we go. Negative 2 gives me an output of 21. And my goal was to have this be less than 0. So certainly false. My next test value is 0. That one I can kind of do in my head. If I put in zeros, I'm just going to be left with negative 15 is less than 0. And that's true. And the last test point I wanted to put in was x equals 2. Get a little help with that one. Gives me positive 21 again. Wanted it to be less than 0, but it certainly is not. So that's going to be false. So as far as my solution, it's only true that that's less than 0 in this little middle section. Just less than, so I'm using parentheses, from negative 1.58 to positive 1.58. Or if I want exact values, from negative square root of 5/2 to positive square root of 5/2. All right, so that's our process. You'll note the similarities to what we were doing with the quadratics, right, in terms of the test values. I was going to take a really quick look at this last graph. Bring that back over here. There are the zeros, just as we found, plus and minus 1.58. And we wanted the function less than 0. So here we are, dips down below the y equals 0, between those two x values. All right, we'll finish out this section with an application problem. So here we go. We're being told that the profit P in millions of dollars made by a t-shirt manufacturer is given by this profit equation, where T represents the number of shirts that we're producing in millions annually. First of all, it says find the p-intercept and explain what it means. So if I want the p-intercept, I'm going to set t equal to 0. And p of 0 would be negative 0 cubed plus 4 times 0 squared plus 0 minus 4, which is just negative 4. So let's see. T is the number of shirts. That says if we produce 0 shirts, we're going to lose $4 million. So presumably you're still bought the factory, you're still paying the bills, and you're still paying your employees, but for some reason nobody's doing any work and we've not got any shirts, so it's all a loss. You lose $4 million. All right, the next question is, for what values of T does the manufacturer actually make a profit? So rather than losing money, when is he going to make money? Well, that's the equivalent of saying, when is this profit equation greater than 0? So I'd like to know, when is negative t cubed plus 4t squared plus t minus 4 positive? Where do I have a positive profit? So let's see. If we use our same method here that we've just been using, start with the related equation. And I'm seeing 4 terms, so I'm thinking grouping. I'm going to factor out a negative since we start with a negative. So let's go with a negative t squared here, which makes that t minus 4. Plus, I'm just going to factor out a 1 there. also times t minus 4. So t minus 4, my common binomial, can be factored out. And then I'd have negative t squared plus 1. So t minus 4 equals 0, or negative t squared plus 1 equals 0. T equals 4, or 1 equals t squared. If I use my square root method here, t is plus or minus the square root of 1. T is plus or minus 1. Now in this particular case, I'm going to have to think eventually. Excuse me. I'm going to eventually have to think about what my reasonable domain is, but for right now I'm just going to do the problem. So let's go ahead and test. My test values are negative 1, positive 1, and 4. So for test values, I'm going to choose negative 2, 0. Oh, I don't know, let's go with 3 and 5. One test value in each section of the graph that gets created. And what I'm testing is again to see when this profit equation is greater than 0. So I am definitely going to put that into Desmos so that I don't have to spend a lot of time doing arithmetic. Get the graph out of the way for now. My function this time is negative, oops, I guess it's actually f of t, negative t cubed plus 4t squared plus t minus 4. I'm going to plug all of my test values into that quickly and easily using a table. Every value I give it, I want it to find f of x1. And the first test value I had was negative 2, which gives me the result of 18. Is that greater than 0? Yes, that's true. All right, my next test value is 0. Again, not a real hard one to do in your head, but we'll use Desmos. We get negative 4 as an output. Is that greater than 0? Certainly not, so this is false. Next test value I picked was 3. My output is 8. 8 is greater than 0, so here we're true. And then this last test value, the 5, gives me negative 24. I'd like that to be greater than 0, but of course it's not, so we're back to false. Okay, so I can see there's actually 2 sections that make the inequality true. But now I need to think a little bit about what T really means. T was the number of t-shirts we're producing. Although my inequality is true here, I can't produce a negative number of t-shirts. So I'm going to say, though true, it doesn't make sense. To have negative number of t-shirts. So I'm basically going to ignore that part of the solution because of the fact that it's not realistic in terms of this problem. That means only this section is actually going to work. So my solution goes between 1 and 4, meaning I want to make between 1 million and 4 million t-shirts. All right, we're going to look at the graph and verify that, and when we do, we can also answer this last question: for what value of t does the manufacturer actually make the largest profit? So I'm going to come back over here, and I'm not going to graph these points anymore. I'm just going to look at the graph. There's 1 and 4, and first of all, you can see that positive profit between 1 and 4. And then right here, in between there, we've got the maximum. So the maximum point is 2.786, comma 8.209. And in terms of my function, what that means is this is my t-shirts, this is my profit. So we make the largest profit, specifically about $8.2 million, if we make 2.786 million t-shirts. All right, so that is section 2.8. It's really what section 2.8 was intended to be about. There's sort of a little addendum at the end of this chapter about piecewise functions, and I'm going to go ahead and record that under 4.8B, although this is really the content of 4.8, but I have to call it something. So we'll see you back for that little piece about piecewise functions for the last graph of this chapter.